Okay, so today we're going to review materials in Chapter 9 for the next exam, and I had the time to go through the key and highlight the ones so I don't have to go to my hard copy and figure out where we are. So if it's highlighted on the board, that's the one we're doing. All right, before we get started, anybody have any specific problems that we need to deal with? I'd like to get those out of the way before I start rambling. Okay. Just looking for chats. Okay. Cheyenne likes to chat. Speak up. Okay. Number one. Consider the calcium metal reacts with oxygen gas in the air to form calcium oxide. Suppose we have this many moles of calcium and this many moles of oxygen gas. How many moles of oxygen left over after the reaction is complete? Okay, what's the first thing we need? A balanced equation, yes. So we're going to start with calcium. That's running. There we go. We have calcium solid plus oxygen gas, and that yields calcium oxide. You have to write it correctly. Remember, oxygen is -2. Calcium is an alkaline earth. It's a +2. So just 1 to 1 is all you need. Okay, so now we need to balance. We could use the budget method, but something as simple as this, really all you need to do is say, all right, I need 2 oxygens, and I need 2 calciums. We're done. Okay, now I put the information from here up here. Extract the information from the problem. Makes it easier to understand. We're given 5.66 moles of calcium and 4 moles of oxygen. And that's moles of oxygen, diatomic oxygen. And the question isn't how much product do we have? The question is how many moles of oxygen do we have left over? So they're telling us that oxygen is in excess. And if we take them at their word, we would expect this one to be limiting. So there's one surefire way to figure it out. How do you change 5.66 moles of calcium to oxygen? Like that. You need a conversion factor to go calcium to oxygen. And the conversion factor is coefficients. That's why you need a balanced equation. So 2 calciums and 1 oxygen here. Okay, so the number of moles of oxygen that we're going to use is from this calculation. So that would be, see if I can do this in my head. 2 and 5 is 2. 2 and 16 is 8. 6 is 3. So 2 times that should be this number. Yep. So this is how many moles of oxygen were used. So what's left over? Is 7, 1, 1. That's how much remains. Oh, 1 second. I must have accidentally punched the button. There we go. Okay. 1.17. There's Michaela back. So 1.17 moles is how much is left over of oxygen after the reaction. The key to a lot of these problems is don't make them more complex than they need to be. They're usually pretty simple. And if they're not simple, you'll find out pretty quick that they're not simple. If you try the simple route, it doesn't work. Okay, so that's number one. Let's go down to the next one. Here we go. Got the whole thing on the board. Number three. Sodium and water react according to this equation. So they're kind enough to give us a balanced equation. So you had one sodium and two sodiums, two waters, gives you two sodium hydroxide and one hydrogen gas. So we got this and this gives this plus this. Without the phases included. What number of moles of hydrogen will be produced when 4 moles of sodium, is added to 1.2 moles of water? Okay, so just to satisfy myself, I usually check to be sure it's balanced. 2 sodiums, 4 hydrogens. So 2 hydrogens here and 2 there is 4. That's right. 2 oxygens, 2 oxygens. Okay, we're good. Whenever you're given, once you balance the equation, if you're given definite amounts of reactants like this, then you can be pretty sure one of them is limiting. So we need to find out which one's limiting. And since we're going to be, the question asks for how many moles of hydrogen do we produce as a product, why don't we use the method where we take this many moles of sodium, say, suppose all of that sodium is converted into hydrogen. How much hydrogen would you get? Sodium, hydrogen. So we have 1 here and a 2 there, which means 2 moles of hydrogen would be produced if we used all of the sodium. What if we used all the water? 1.2 moles of water. So we have water down here, hydrogen up here again. So that's 1, that's 2. And that's 0.6 moles of hydrogen. So now we can tell at a glance which one is limiting. Water's limiting. That means we go with this answer. That's how many moles of hydrogen you can produce from that reaction. And that's why the answer is 0.6 moles. All right. 3. Let's go to the next highlighted one. Okay, I better scroll that one a little bit. Chop off the bottom answer. Even though the bottom answer is not the right one. Suppose we don't know that. Okay, in this reaction, which looks familiar, nitrogen plus hydrogen yields ammonia. That's Haber's reaction. How many moles of ammonia will be produced from 1.21 moles of hydrogen and excess nitrogen? Actually, this is a simpler problem than the one we just did. With this balanced equation, there we go. We're given 1.21 moles of hydrogen, 1.21 moles, and excess nitrogen. How many moles of ammonia will be produced? That's pretty straightforward, I think. Right. We're just converting this much hydrogen into ammonia. So if we're going to have ammonia as our answer in the numerator, hydrogen in the denominator, all we need is the coefficients. 3, and 2. So what's 2/3 of 1.21? Do you get your fraction fixed? Okay.
Yeah.
Let's see, we're starting off with 3 significant figures. So what does that leave us? 0.807. 0.807 moles of ammonia. Okay, that's number 5. Let's see. 6 and 7, we got them both on the same page. All right, consider the following unbalanced equation. All right, and I put that in bold letters to call your attention to the fact that it's not balanced yet. If 1.7 grams of ethanol, which is this one, that is ethanol, reacts with 11.2 grams of oxygen, how many moles of carbon dioxide are produced? Okay, so first thing we need to do is balance the equation. And we're going to burn ethanol. It gives us CO2 and water. So maybe we better do a budget for this one. So we have carbon. Let's see, is it showing up on? Yeah, let's figure it out. We have carbon, hydrogen, and oxygen. And that covers all our bases. So on this side, we're starting off with 2 carbons, 5, 6 hydrogens, 1, 2, 3 oxygens. On this side, we got 1 carbon, 2 hydrogens, and 2, 3 oxygens. Let's see if I counted right. 2, 7, 8, 9, 10, 11. 9, 10, 11. 1, 2, 3, 4, 5, 6, 6. Okay, we're good. Now, where do we start? Well, we typically want to hold the oxygen out because it's a single element. So I would just go down the line and say, okay, we've got 2 carbons over here, we need 2 carbons over here. That changes our oxygens to 4 plus 1 is 5. Okay. Now we need hydrogens. We need 6 hydrogens on this side. Okay. So if we put a 3 in front of that one, that'll give us 6 hydrogens. But that changes the oxygens again. So we have 3 plus 4 is 7. Okay. Now, what should we do next? You can't multiply anything times 2 and get an odd number. Right. We're going to use the fraction trick. So 7 halves would give us 7 oxygens. Okay. Now, just to be consistent, we want to make all the coefficients whole numbers. To work the problem, actually, you don't need that. You could work it from here because the ratios now are established. It's 1 to 7 halves to 2 to 3. That ratio is fixed now with a balanced equation. So we could use this if we wanted to. But to be consistent, let's get rid of that fraction. So that makes 2 here. That makes 7 there, 4 here, and 6 there. So now let's go to the rest of the problem. 1.7 grams of ethanol, 1.7 grams, and 11.2 grams of oxygen. Okay? And the question is, how many moles of carbon dioxide will be produced? So we're looking for moles of carbon dioxide. Right? This is a limiting reactant problem. We've got two fixed values here, given values for both of the reactants. One of them is going to run out first. So remember, the only way we can go from here to there is make moles. You can't go there with grams. The balanced equation doesn't intrinsically say anything about mass. It's talking about numbers, moles, 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 moles. So we need a molar mass for ethanol in order to convert 1.7 grams into moles. So you got to go to your periodic table and you need 2 carbons, which is 12.01. Let's do it this way. Okay, that's the carbons. We got 6 hydrogens right there, and we got 1 oxygen. There we go. So now we can have 6.06, 16, and I get 46.80. Yep, 46 point. I must be dyslexic. 08. There we go. And this is grams per mole. So this would go here. And we divide that number into 1.7. And I get 3.689 times 10 to the minus 2 moles of ethanol. Let's try that again. My abbreviation for ethanol, ETOH. The OH stands for the alcohol part, and the ET stands for the ethanol part. Okay, so now we know how much, how many moles of ethanol we have. How many moles of oxygen do we have? 11.2 grams. And we need to convert it to moles. Right, remember the molar mass of oxygen? 16 for 1 oxygen. We got 2, don't we? 32. Needs to be 32 grams. So 32 divided into 11.2. Equals, must be consistent. This is, I put this in scientific notation. Let's put the oxygen. 3.50. 3.5. I can't write today. 3.50 times 10 to the minus 1 moles of oxygen. Okay, so now that we have a number of moles, we can find out how many moles will each one of these produce of carbon dioxide. So if we have 3.689 times 10 to the minus 2 moles of ethanol, we need a conversion factor that will take us from ethanol to carbon dioxide. Coefficient of carbon dioxide is 4. Coefficient of ethanol is 2. Okay. If we had not changed that fraction, it would have been 2 here and 1 there. 2 to 1, and the same thing is 4 to 2. Okay, so what do we get? 2 times that value? I got 7.378. 7.378. Let's see. 7.378 times 10 to the minus 2. moles of carbon dioxide. Okay, so we do the same thing for oxygen. 3.50 times 10 to the minus 1 moles of oxygen. And then we need to convert this one from oxygen to CO2. So the coefficient here would be, again, 4 for CO2, and oxygen now would be 7. If we hadn't removed the fraction, then this would be 2, and that would be 7/2. Right? So if we look at that, if this were 2 and this was 7/2, what's that? Well, the 2 in the denominator of the denominator is the numerator. So 2 times 2 is 4, divided by 7. That's what we got there. I'm just proving to you that you can work the problem without going through the fraction removal process. It would still work. The ratio is the important thing. Okay, so 4 times that value divided by 7. And I get 2.00 times 10 to the minus 1. 2.00 times 10 to the minus 1 moles of CO2. All right, so which one's limiting? Ethanol is limiting. Right. This one's minus 1, 10 to the minus 1. This one's 10 to the minus 2. So this is the amount in moles. And since all the answers are in standard notation, we have to convert. Okay. So we move the decimal place 2 to the left, and we get 0.0738, 0.073, or maybe 0.074. 0.0738, here we go. 3 significant figures. All righty. That was a little more complicated. How about 7? Fe2O3, I'm going to give you the molar mass, reacts with carbon monoxide according to this equation, which appears to be balanced. When 185.5 grams of carbon monoxide reacts with excess iron 3 oxide, how many moles of iron will be produced? Okay, so here's our equation. Fe2O3 plus 3 carbon monoxide yields 3 carbon dioxide plus 2 iron. Okay, double check myself. Okay, if we're given 185.5 grams of carbon monoxide, 185.5 grams of carbon monoxide, and excess iron 3 oxide, how many moles of iron are produced? So the question is moles. Right? How do we get from one side to the other? Got to have moles. So we have to convert this to moles. Right? Grams and moles in a quotient means molar mass. And the molar mass has been given to us for carbon monoxide. Carbon monoxide, 28 grams per mole. So that tells us, once we do the calculation, 185.5 divided by 28 is 6.625. 6.625 moles of carbon monoxide. That's 4 significant figures. We keep all of them. Okay, so now to answer this question, we need to convert that many moles to that many moles. Okay, and the conversion factor is in the balanced equation. Carbon monoxide is 3, iron is 2. So we take 2/3 of that value. And I get 4.41, we're significant, 4.417. Moles of iron. And off by just a hair. So what's my rule with multiple choices? You can't choose the best one, right? Now, if one of these had been none of the above, then you could legitimately say none of the above, because your answer is this, and then all you have to do is show me your work, and that proves it to me, and you get credit for it. But if my key says that this is the right answer, and you pick that answer regardless of whether you're exactly on the answer, then it just goes through automatically. But there's always room for argument if you've got a case to make. That was probably a rounding error. Okay, you probably noticed this one intentionally left blank. It's one of those cases where I threw that one out after I'd already produced the worked problems. And I didn't want to have to go back through and rework all the problems and renumber them. So I just ditched that one. And the worked problems, number 9, should also be. Well, no, number 9 is there. No, that's number 14. Number 9 is delete, yeah. Okay, number 9 is missing in the work problems too, which is as it should be. Number 10. Using this following equation, ammonia plus oxygen yields nitrogen dioxide and water. How many moles of ammonia will be required to produce 11.9 moles of water? Okay, so here's our balanced equation. Oxygen and nitrogen dioxide and water. 6 water. So what are we given? We want to produce 11.9 moles of water. 11.9 moles of water. The question is, how many moles of ammonia does that require? That's pretty simple. Now, at this point, we're assuming that this is all 100% conversion. This is theoretical. We haven't gotten into all to the efficiency calculations yet. So this is a simple unit conversion, actually. That many moles of water. Water, ammonia. So we have 6 waters and 4 ammonias. So 2/3 of 11.9. And I get 17.3 significant figures. 17.5. That's how much ammonia will be required to produce this many moles of water. And what did I do wrong? None of these. Did I do it? Wait a minute. Yeah, I did calculate it wrong. Yep. 7.93, right? There we go. All right. That's 10. And 13. I got to scroll down. Consider the following unbalanced equation. If 3.09 moles of silicon were produced, how many moles of sodium fluoride were also created? Okay, so the balanced equation, the unbalanced equation is, let's see, 2SiF. That's sodium hexafluorosilicate. Sodium yields silicon plus sodium fluoride. Okay, so now we need to balance it. I didn't leave myself any room there. There we go. Okay. I wonder if we can do this without using the budget. 2 sodiums. Oops, sorry. 3 sodiums. No, it's the wrong place to start. Start with fluorine. 6 fluorine. There we go. That means we have 6 sodium. I better do a budget. This is more complicated than I thought. Sodium, silicon, fluorine. Okay. 2 sodiums. 3 sodiums. All right. Wake up, Dave. 3 sodiums, 1 silicon, 6 fluorine. That would be 10, 2, 3, 10, that's right. And this one has 1 sodium, 1 silicon, 1 fluorine. Okay. So starting with fluorine was probably a good idea. That changes the fluorines to 6 and the sodiums to 6. Okay. Now we need sodium. We need 6 sodiums on this side. So I would think leave that sodium alone and fill in the sodiums with this one. So if we put 3 here, that means 3. Oops, sorry. 4, right? Yeah, 4. 4 plus 2 is 6. There we go. Did I lose anybody? Okay. Now we've got a balanced equation. We can proceed to the rest of the problem. If 3.09 moles of silicon are produced, 3.09 moles. How many moles of sodium fluoride were also created? Oh, okay. So if this is silicon, then we just need to multiply it by the ratio. 1 silicon, 6 sodium fluoride. Right? So actually, you don't need a calculator if it's multiple choice. You say 6 times 3 is about 18. So the answer should be 8. I mean, if you're taking a test, you're in a hurry. That's what I do. Now, if one of the answers was none of the above, you'd have to do the calculation to be absolutely certain. Or if there was another one that was really close, like 18.4 or 18.6, then you would have to do the calculation in order to discern between the two. All right, let's see. There's another that I threw out. 18. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum to oxide? Okay. The clues here are that it's a decomposition and it produces atoms of aluminum. So if we're going to have a decomposition, you know that we've got this one as a reactant. And if it decomposes, it's going to produce aluminum and oxygen. And this is a tricky one too. You got to remember that oxygen is diatomic. Okay, now we just need to balance the equation, which should be fairly simple. We need, here's a case. We're going to use the trick, the cross multiply. Because you've got 2 here and 3 here. We'll put a 2 here and a 3 here. That means 6 oxygen, and 4 aluminum. So that should balance. You can do the same thing with the budget if you want to. Draw out the budget. Decomposition of 31.5 grams. And we want to know how many atoms of aluminum. What question? Atoms. Okay. Right, just like always, balance the equation, and then if you've got mass, you got to convert it to moles. So we need the molar mass of aluminum oxide. Okay. 2 aluminums, 26.98. Let's do this. 2, 26.98. And then 3 oxygens. Yeah, that'll be the molar mass of aluminum oxide. Okay, I get 101.96 grams per mole. Divide that into 31.5. And I get 0.3089. 0.89 moles of aluminum. Okay. Now, how do we convert moles to atoms? Exactly right. Avogadro's number. So this one is going to be multiplied by moles on the bottom, atoms on the top. So this means 6.022 times 10 to the 23rd. So 0.3089 times 6.022 10 to the 23rd. And I get 3 significant figures. 1.86 times 10 to the 23rd atoms. 1.86. What did I do wrong? Oh. Huh. I'll tell you what. It's a good thing I don't have to take my own exam. That's not aluminum. That's aluminum oxide. Correct? This molar mass for that convert that to aluminum. Now we have to convert this to aluminum. Okay. Now skip the step. 4 there, 2 there. So this is going to be 0.6, 8, 17, 1 moles of oil. I think that's right. Okay, now we can convert. To atoms. There. 0.6178, 6.022, 3.72. Atoms. You know, I could have corrected that mistake once I found out that I was wrong there. What I was actually doing was saying, how many atoms of this? And since the ratio is numbers, right, this is twice as many atoms as that, I could have just multiplied that answer times 2 and got this. And that would have been correct. So there's more than one way to solve that problem. I just wanted to go back and do it the correct way, rather than fixing a problem in midstream. All right, 18. We got some redundancy here, so we'll skip a few. 23. Calculate the mass of water produced when 9.47 grams of methane, CH4, react with an excess of oxygen in the following unbalanced equation. Mass of water produced. Okay, so we need to balance this equation. CH4 is methane plus oxygen yields carbon dioxide. That's water. So I leave myself in space here. There we go. Remember what I said about hydrocarbons. Whenever you're reacting with oxygen, you're going to have to use the fraction trick, except for methane. You won't have to use the fraction trick for methane. We can probably do this one without the budget. If I need 4 hydrogens, that gives me 2, still got 1 carbon, 4 hydrogens. Now I've got 2 plus 2 is 4 oxygens. There you go. That should do it. Okay, so now what do we get? 9.47 grams of methane. Okay, excess oxygen. All right, and the question is, mass of water produced. How many grams of water is produced? That's not right. How many grams of water are produced? Oh, on my high school English teacher roll over in her grave. Okay, so methane, we need molar mass, correct? Let's see, did we get another one? We did. Got another one. Jessica. Okay. So we need molar mass to convert methane to moles of methane. So 12.01 for carbon and 4.04 for 4 hydrogens is 1605. Okay, cancel the grams and divide that into 9.47. And I get 0.590, 0.950 moles of methane. And we want grams of water, 0.950 moles of methane. We got to convert that to moles of water first. Right? We couldn't get there from grams. We had to make moles. Now we can go to moles with the coefficient ratio. So 2, 1. All right, just 2 times that number, right? So I get 1.18 moles of water. Now to convert moles of water to grams, we need molar mass again. This time, we need molar mass of water. Remember what that one is? 18.02. Times 1.18. And I get 21.3. Very significant figures. Grams of water. Is that what it was asking for? There it is, 21.3. Had me second guessing for a minute because one of them is scientific notation. All right. Let's see how we're coming along here with not quite an hour yet. I think we're good. 26. Following an unbalanced equation, how many moles of water are needed to react with 206 grams of aluminum carbide? Okay, so we need a balanced equation. Al4C3. Al4C3 plus water yields AlOH3 plus methane. I should have started further to the left. Let's try that again. Okay. Water, aluminum hydroxide, and methane. Okay. This is one of those cases where carbon, remember if you work from the right and you go halogens, chalcogens, nicogens, carbon group, you would expect to see -1, -2, -3, -4 for carbon if you go that way. But if you go from the left, you would say +1, +2, +3, +4. So carbon's in the middle. Carbon can be actually 9 different oxidation states. In this case, it's a minus. It's a -4. And aluminum is always +3. So that's where you get the balance. 12 + 12 - 12. And since carbon is in the anion position, we call it carbide. Right? Just Change the ending to IDE. Okay, now back to the question. 206 grams of aluminum carbide. 206 with, that's it, grams. And we want to know what, how many moles of water are needed? Question, moles. Okay. So what we need is a balanced equation. Right? Probably ought to do a budget. Let's see, can I write? Yeah, I got to write it. Aluminum, carbon, hydrogen, oxygen. So we're starting off with 4 aluminums, 3 carbons, 2 hydrogens, and 1 oxygen. Over here we have 1 aluminum, 3 oxygens, 3 hydrogens. Oops, no. How many hydrogens? 7 hydrogens. 4 plus 3. And 3 oxygens. Excuse me, I got oxygen already. Carbon, 1 carbon. Okay, that's where we're starting from. All right, we don't have any free elements here, so we can't hold any in reserve. Let's see. We got hydrogen in 2 different places there. We probably don't want to mess with that one just yet. Carbons, perhaps. I would, in this case, I would just start from the top. Say 4 aluminums. Right there. That gives us 3 times 4 is 12 oxygens. And 12 plus 4 is 16 hydrogens. Correct? Okay. Now, what about carbon? Let's see, we've got 3 carbons on this side. We do 3 carbons on that side. That changes the hydrogens again. So we have 12 plus 12 is 24 hydrogens. Okay. So now, oh, this is beautiful. This is beautiful. 24 to 12 is 2 to 1. 2 to 1, 2 to 1. All we need here is to balance the hydrogens and the oxygens will fall into place. So if we have 12, that makes 24 hydrogens and 12 oxygens. Sometimes they just work out. Okay, now that we've got a balanced equation, we can work on the stoichiometry. How many moles of water? So we've got to convert aluminum carbide into moles. Let's see, 4 aluminums, 2698. So 4 times 26.98. And then 3 times 12.01 will give us the molar mass of aluminum carbide. And times that, add together, I get 143.95. Okay. So 206 grams times, this is grams on the bottom, moles on the top. So 143.95. Let's clean this out here. Divide that into 206. And I get 1.43. 1.43 moles of aluminum carbide. Okay, now we need moles of water. Carbide and water. So we cancel the aluminum carbides. And the ratio then is 12 to 1. So 12 times 1.43. I get 17.2 moles of water. Right here. Okay. That was 26. Let's see. Go. Yeah, that's everything. Okay, for this one, 29 is this problem, and we'll work it. But I thought it might be interesting to try this one as well. So we'll do both of those. And this one doesn't have an answer on the key. That's just something that kind of interesting. Okay. So consider the following reaction where X represents an unknown element. So we have 6 X's plus 2 diboron trioxide yields tetraboron tri-X plus 3 XO2s. Okay, so we need, and it looks like that one's balanced. 29. So 2 B2O3. Oops, I left one out. Sorry. Back up. 6X plus 2 B2O3 equals B4X3 plus 3XO2. There we go. Now, the question is, what's the identity of X? And we're given 165 grams of X, 65 grams of X, reacts completely with diboron trioxide. So this is in excess to produce 2.29 moles of this one. 2.29 moles of that. And it just kind of leaves that one hanging on the end. Okay, I think we did one of those Tuesday. What do you need to identify X? 2 possibilities, right? Right. If you have the number of protons, if you have the atomic number, it's simple. Just go to periodic table. But if you don't, the backup position is molar mass. If you know the molar mass of the element, you can, for all but a couple elements on that table, the molar mass is unique also for that element. So in order to find the molar mass, we need mass divided by moles. Right? Mass of X divided by moles of X will give us the value that we need to look it up on the periodic table. We have the mass. What we need is the moles. So if this is a balanced equation, and it appears to be 2 boron, 2 boron, 6X, 3 plus 3 is 6X, 6 oxygens, it's balanced. So what we can do is say, if we know this, 2.29 moles of B4X3, we can convert that to moles of X. Right? That's 6, that's 1. So 6 times that is the number of moles. I got 13.74. Okay, so 165 grams, 13 point, what did I say, 64? 74. 74 moles will give us the molar mass of X. 0.65. Got that into it. So I got 12.01. Right. And we don't even have to look that one up. That's carbon. Yep. Okay. So that's the one that's labeled 29. I want to do that extra one. So how about this one? X plus 3F2. X plus 3F2 yields XF6. Okay. X is 235.2 grams. Let's see, is that balanced? Yeah, that's balanced. We want to find out what this element is. So we got 235.2 grams of X produce 347.9 grams of XF6. Okay. What I should say is this is excess. You have to assume that. Right? This is not limiting. So from this number of grams, we get that number of grams of product. Okay, let's see. We got the mass. We need the moles. We need the moles of this. We can't convert that directly into this one. We can't convert that into moles and use the same trick as the previous problem and go back like that. But what we can do is use conservation of mass in a reaction. Right? If this combines with that to produce that, this mass has to be equal to those two together. Right. So 347.9 minus 235.2, 7211 grams of F2. Okay, is that right? 9, 7, 4, 3, yeah. So now that we know mass of fluorine, we can find out how many moles that is and then translate that into moles of X. We just need the molar mass of F2. 1938. 38 would be F2. So 38 divided into 112. 112.7. And I get 2.966. 2.966 moles of F2. Now we can convert that to moles of X. Because we know the ratio. 3 of these for every one of those. So we divide 3 into 2.966. And we get 0.989. 0.989 moles of X. Now we've got the information we need. 235.2 grams per 0.989 moles. 235.2 divided by that number. 238. 38 grams per mole. Now we just have to go to the periodic table. Go to the periodic table and follow it down until you find 238. And the closest one I can see is uranium. Okay. So the twist on this one was we weren't given enough information to work backwards directly from, let's see, we were given we were actually given moles of that thing right there. If we had this problem set up the same way as that one, then instead of moles of B4X3, we would have been given we would have had to been given mass of this one and mass of that one, and then work backwards to this one. So it would have been a steeper climb. But I just wanted to show you that there's more than one way to skin a raccoon. I don't skin cats.
All right, thanks. How does that recommend work?
Let's see. Skin a possum. How about a possum? Yeah. Nobody likes possums. Oh, smiley. Here we go. 32. Which of the following reaction mixtures would produce the greatest amount of product, assuming all went to completion? Each involves the reaction symbolized by this equation. So we got the Haber equation again. 3H2 yields 2 ammonia. Okay, so let's say we're going to have to do them B, C, D, E. All right, if we got 1 mole of that and 3 moles of this, okay, how many moles of that would be produced? Well, 1 to 3 to 2. Right? That's a stoichiometric mixture. How about 5 moles of this and 3 moles of this? This is excess. You only need 1 of these. You got 3. So you can still only produce 2 moles of ammonia. We have to skip C because we can't answer it until we do the others. So 1 mole of nitrogen and 6 moles of hydrogen. Now, hydrogen is in excess. We've only got 1 mole of nitrogen, which would also produce 2 moles of ammonia. And with 3 moles of nitrogen and 3 moles of hydrogen, nitrogen again is in excess because it needs to be a ratio of 1 to 3. So this one's excess, this is limiting. 3 produces 2. So the answer is C. All would produce the same amount of product. All right, let me scroll 33 up there. Go. Balanced equation. P4 plus 6 hydrogen yields 4 pH3 tells us that 5 moles of hydrogen. Okay, equation. P4 plus 6 hydrogen yields 4 pH3. That's 4 pH3. Yeah, that's balanced. 5 moles of hydrogen tells us that 5 moles of hydrogen would do what? Cannot react with phosphorus. I don't think so. The equation itself tells us that could happen. So A is wrong. B reacts with 2.5 moles of P4. Okay, so we got so many moles of P4, so many moles of pH3, so many moles of pH3, and so many moles of P4. So I think the most efficient way to work this problem is to say, convert this to that and convert that to that. 5 moles of hydrogen would produce how much pH3? Right, we have 6 here, 4 there. So 2/3 of 5. I get 3.33. Well, 3.3 moles of pH3. Oh, there it is. Since there's no, we found the answer. We can stop there. What I was going to do is say, how much P4 would be required? Because P4 is a possible answer, but the ratio is 6:1. So 6 divided into this would be less than 1, and that can't possibly be the right answer. That can't be the right answer either. Too big. So we got our answer. Okay, let's see. 39. Consider the reaction of magnesium metal with hydrochloric acid. Ooh. Magnesium plus hydrochloric acid, that would have to be aqueous. This would have to be solid. Yields what? Magnesium chloride and hydrogen gas. Magnesium chloride and hydrogen gas. Okay. Let's see. That's -1. This is +2, so you need 2 of those. And write the compounds correctly. And then we need to balance it. Let's see. I think I can do this with one number. 1 magnesium, 2 chlorines, 2 hydrogens. It's balanced. Okay, if 4.52 moles of magnesium, 4.52 moles magnesium, and 4.52 moles of hydrochloric acid, okay, are reacting. How many moles of hydrogen gas are produced? We got a limiting reactant problem here. So what we need to do is convert this to moles. 4.52 moles of magnesium. Grams, moles, so the grams cancel. Wrong. And you know what? I don't need to do that. What am I thinking? It's already moles. 4.52 moles of magnesium would produce how many moles of hydrogen gas? Okay. 1 to 1. 4.52 moles of hydrogen. Whereas 4.52 moles of hydrochloric acid converted to hydrogen gas is a ratio of 1 to 2. So that would be, let's see, 2.26 moles of hydrogen. So the limiting reactant is hydrochloric acid, and it only produces 2.26 moles of hydrogen. I broke my own rule. I said, don't make it more complex than it has to be. And I immediately started to make it more complex. It's already in moles. That's 39. Let's see. Oops, too far. Yep, we got that one. So for this following equation, we're going to burn ammonia and produce nitrogen dioxide in water. How many moles of water are produced from 9.12 moles of nitrogen dioxide? It's like we're working back. They're getting easier. So we have 4 ammonias, 7 oxygens, 4 nitrogen dioxide, and 6 water. And we're given 9.12 moles of NO2 given off. 9.12 moles. The question is, how many moles of water are also produced? So this is a simple conversion, actually. That many moles of NO2 have to be converted to water. With a 4 here and a 6 here, we need 3/2 of 9.12. And I get 13.7. Pretty significant figures. Is that the question? How many molecules of water? Okay, so I'm not done. Hey, Avogadro again? Keeps cropping up. 6.022 exponent 23. I think I got a rounding error in here. Let's see. 8.24 times 10 to the 24th. 10 to the 24th. Molecules. Nope, came out all right. Okay, that was 43. Go. $45. Fluoride is added to some dental products. Can we do one of these in class? How many grams of 10,2 fluoride can be made from 49.6 grams of hydrogen fluoride? If there's plenty of 10. All right. So it looks like the equation's balanced. N, 2F, 2 hydrogens. Yeah, we're good. How many grams of 10,2 fluoride can be made from 49.6 grams, 49.6 grams of hydrogen fluoride, if this is excess? There we go. So, first things first, the equation's balanced. Second thing, convert this to moles. So, fluorine is 19 and hydrogen is 1.01. So 20.01, right? So we divide 49.6 divided by 20.01. And I get 2.479. 2.479 moles of HF. Okay. Now we got to convert it to 10,2 fluoride. Okay, ratio is 1 to 1. 479 moles of into fluoride. Then we got to convert that to grams. Moles on the bottom, grams on the top. So we need a molar mass of 10,2 fluoride. Let's see, fluorine is 19. So that's 38 for fluorine. And then 10 is 119.71. So I get 156.71. There we go, times 2.479. Is 300, let's see, three significant figures. 388 grams. Right here. Okay. That was 45. And there was another blank one. Let's see, must have a lot of redundancy. Here we go, 60. Let me scroll that one a little bit. Got the top of his head chopped off. Yeah, we can get both of them in. 60. Consider the following reaction. Okay. Much as I hate to, let's go ahead and do it. 2 A's plus a B yields 3 C's plus a D. Okay, 3.35 moles of the A. 3.35 moles of A. And 2 moles of B react to form 4 moles of C. So this is actual. Question is, what's the percent yield? This is like, I think I mentioned this at the end of Tuesday's lecture. If you're confronted with a problem that's asking you a question that doesn't quite fit the narrative, because we had actual mass divided by the theoretical mass times 100 is percent yield. But in this case, we're going moles ratio. And since that's all the information you're given, you have to go with it. So if this is actual moles, we just need to find out what is the theoretical moles of C. Right? And we can do that from here. But these are given amounts, so one of them is going to be limiting. So how many moles of C can be produced from A? So moles of A produces C, that's 2 and 3. So 3 halves of 3.35 would be 5.03. So this would produce 5.03 moles of C. How about B? Okay, so we're going to get rid of B, make C. C is still 3, B is 1. So 3 times this, 6. Right, so now we know which one's limiting. That's the theoretical amount for C. So now you just need the actual divided by the theoretical times 100. And let's see if I did it right, 80%. Or 79. Actually, I rounded off too much. My calculation says that's 79.5. So the closest one is 79.6. '61. Calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. So we have 2 sulfurs and 3 oxygens. Looks like a synthesis reaction. 2SO3. 25 grams of sulfur. And where the question is molecules of oxygen. Okay, so we got to find out how many moles of this is to find out how many moles of that there are. Conversion. You know what? Do it in one step. This gives us moles of sulfur. 3206, 3207, rounded off. So 3207. Okay. That gives us moles of sulfur. How about moles of oxygen? Sulfur, oxygen. So we have 2 here, 3 here. Okay. So that gets rid of this one and this one. Now we can convert moles of oxygen to molecules. Oh. 6.022 times 10 to the 23rd. So now we've done all the thinking. We just need to say 25 divided by 32.07 times 3 divided by 2 times 6.022 times 10 to the 23rd. And I get 7.04 times 10 to the 23rd. Right here. So we did it in one step. We could have strung it out, right? And that may have been the way. 61, did I do it that way? I did it in steps. Yeah. 61, I did it in steps in the worked problems. Here, I put all those steps into one calculation. All right, 61. Let's see. There's another one. Kicked it out. Oops, 69. Yep, 69. Let me just have to scroll that one just a tad. See if I can get these two. Yeah, that's going to be close. Yeah, there we go. 69. In the reaction between carbon monoxide and Fe3O4, the theoretical yield in an experiment is calculated as 47.2 grams. 47.2 grams theoretical yield. Theoretical iron. When a careless chemistry student carries out the experiment, actually gets 37 grams actually. Oh, they just want to know, this is simple calculation, percent yield. So divide that one by the actual, the actual by the theoretical, and then times 100. And that should be 78.4%. I didn't go through the rigmarole because it's too simple. Is it actually 78.4? Okay. $70. 3.1 mole sample of potassium chlorate. That's a polyatomic ion, ClO3, with a -1 charge plus potassium. You only need one of each. Decomposed according to this equation. How many moles of O2 are formed assuming 100% 100% yield. We used to take potassium chloride in solution and dribble it on the floor. When it dried, it made a powder, which was pressure sensitive. So when somebody stepped on it, it would decompose into potassium chloride and oxygen gas. The oxygen gas would make a pop. So somebody would walk across the floor and step on one of those white spots, and it'd go pop under their foot. Wouldn't do any damage, but it would shock them. Chemistry tricks. Okay, so we've got this equation, 2KClO3 yields 2KCl plus 3O2. And how many moles of oxygen form? 3.1 moles of this one. Right? Is decomposed. How many moles of O2 are formed? Assuming 100%. Oh, this is a simple conversion. So this one is KClO3, this one is oxygen, right? And this one is 2, that was 3. So 3 halves, or 1.5 times that, would be 4.65. Or 4.7, rounded off. All right, 71. When 3.4 moles of iron react with chlorine, according to this reaction, which is balanced, how many moles of chlorine are required to react with all of the iron? Okay, so we've got 2 irons and 3 chlorines. Yield 2FeCl3. And we're given 3.4 moles of iron. Question is, how many moles of chlorine are required? Oh, 3.4 moles of iron. Okay. Got 2 here, 3 there. So we need another 1.7. 5.1 moles of chlorine. Here we go. You almost do that one in your head. Okay. Oh, 72. I need to scroll that one. 73. It's gonna be close. Nope, can't do it. Let's go like that. And when I page, the other one will come right up. 72. Ammonia reacts with oxygen to form nitrogen dioxide and water. According to this balanced equation, if you react ammonia and oxygen, and at the end of the experiment, you find that you produce 23 grams of water and have 8.52 grams of ammonia left over, what's the mass of oxygen reacted? Okay. This looks like a real hairy problem, but it's not. I've got the balanced equation already. Okay. What information are we given? At the end of the experiment, you have produced 23 grams of water. Okay. And have 8.52 grams of ammonia left over. So we have so much ammonia minus a certain amount yields 8.52 grams of ammonia left over. This is remaining. Determine the mass of oxygen reacted. What that means is this is limited because you have excess here, right? Okay. So that is all you need from this information. You don't even need the mass of ammonia because we're going from here to here. What's the mass of oxygen reactant? So we just need to convert this 23 grams of water into moles of water. Okay, 18.02. I get 1.276. 1.276 grams of water. Oh, excuse me. Moles of water. Moles of water. Now we convert moles of water to moles of oxygen. Let's just write it this way. Water, oxygen. And the ratio is 6:7. So 7/6 is 1.489. 1.489 moles of oxygen. Now we can find out what mass of oxygen. We just need to know the molar mass of oxygen, 32 grams per mole. So 32 times that number, 47.3 significant figures, 47.7. Grams of oxygen. Here we go. Okay, that was 72. And let's see, page to 73. In this reaction, C2H4, I think that's ethylene, burned with oxygen is a combustion reaction, makes carbon dioxide and water. 5.5 moles of carbon dioxide are produced. How many moles of oxygen were reacting? Oh, it's already balanced for us. That's good. Okay. C2H2 plus oxygen yields carbon dioxide plus water. And that's 2, 2, 3. And we're given 5.5 moles of CO2. Are produced. How many moles of oxygen are reacting? That's fairly simple, right? CO2. Go. 3 from here, 2 from there. 1.5 times that. I could do that in my head, but I'm not going to. 8.25 or 8.3, rounded off. Was that the question? How many moles? Okay. Closest one, you could say none of these. Right? If you came up with that that value. But the best answer is 8.2. It must be a rounding error. Let me see, I'm trying to get 5.5. 3 times 2 divided would be 8.3 rounded off. Yeah. Probably ought to change that. But this is in the review document. We wouldn't want to be concerned unless it showed up in a test. 75. Okay, still got time. Unbalanced equation. We balanced this one before. 1.86 grams of ethanol reacts with 14.3 grams of oxygen. How many moles of water produced? Okay. C2H5OH plus O2 equals CO2 plus water. I don't have to go through that again. We've already done it once. 3, 2, 3. 1, 3, 2, 3. 2 carbons, okay. 6 hydrogen, okay. 1 plus 7. 4 plus, okay, we're good. All right, now what are we getting? 1.86 grams of ethanol. 1.86 grams. React with 14.3 grams of oxygen. How many moles of water are produced? We've got a limiting reactant here somewhere. So we have to calculate it again. 4608, 1.86, 46.08 grams per mole is the molar mass of ethanol. So let's say put it in standard notation. 0.0404. 0404 moles of ethanol. And oxygen converted would be 32. 14 divided by 32, 14.3 divided by 32 would be 0.447. 0.447 moles of oxygen. Now, which one's limited? Well, this one's, for every one of these, you get 3 of those. So you have 3 times this, 0.1212 moles of water. And this one's 3 to 3 or 1 to 1, so you have 447 moles. Yeah, so this is the limiting one, and that's the answer. 1, 2, 1. Did I lose anybody? I kind of, rather than write it on the board, that's sort of just logic. Ratio is 1 to 3. So if you got 1 of these, 3 of those would be water. Okay? I want to be sure we finish before the time runs out. Okay. 80. 22.5 grams of nitrogen with 22.5 grams of hydrogen. Determine the mass of ammonia that can be produced from these 2 reactants. Nitrogen gas and hydrogen gas yields ammonia. And it doesn't balance it for you, so you've got to balance it yourself. Now I'll do it. Now we're told 22.5 grams of each will produce how much ammonia? So for nitrogen, 22.5 grams per mole, produce how many moles of nitrogen? That's 28.02. Because each nitrogen is 14.01. Okay. Divide 22.5 by 28.02 is 0.803. 0.803 moles of nitrogen. And since it's for every one of these, you get 2 of those, you should get 1.606 moles of ammonia. For hydrogen, 22.5 grams, it's going to be a whole lot more moles, 2.02 grams per mole. I think I can see where this one's going. That's 1.11 moles of hydrogen. The ratio is 3:2. So for every 3 of those, you get 2 of those. So 3/2 of this. Would be 1.67. So this ought to be, oh, we got to convert it to grams. 1.606 moles. See, did I do this one right? No, I didn't. It's 2/3. Right? Hydrogen on the bottom, ammonia on the top. 2/3. I have to do that one again. 0.74. 0.74 moles. Okay. So this is the limiting one. Moles on the bottom, grams on the top. Nitrogen is 14.01 plus 3.03, 17.04.
If you have your 11, the 1.11 is supposed to be 11.14.
You're exactly right. Okay, so back to the drawing board. 1.606 is the limiting one. This one. Okay. Now, let's see. I need to switch back to this one. It's 28.4. Did something wrong. 1.606.
I think you need that 6 on it. 606.
This one. Well, if that'll make a difference. Let's see, I calculated ammonia right. 14 plus 3 is 17. Yeah, that's right, 1704. 27.4. There we go. Okay. That was 80. 83. Let me see, how are we doing on? How many more do I have picked out? 83 and 84. Okay. We can get it, I think. Fe2O3 reacts with carbon monoxide. According to this reaction, we did one of those earlier. 470 grams of Fe2O3 react with excess carbon monoxide. What number of moles of iron? I don't even think we need to do this one. Right? All you need to do is convert this into moles and change that number of moles to that number of moles. And you got your answer. Okay? If we need to, I'll come back to it. A4. Which of the following statements is always true concerning the reaction represented by the following balanced chemical equation? Okay. This is ethane burned in oxygen. There should be a plus sign right there. Yields carbon dioxide and water, and that's balanced. So, that's out of place. This should be down here. That's a mess. Let me make a note. Fix that. 84. That makes no sense. Well, that's my key. How's the, it's the same in the unkeyed one? I got it flipped around. Yeah, okay, that needs to be correct. Let's see, this needs to go down here. And then that would make the answer D. Okay. So let's look at B, C, D, and E as presented here. Okay, for B, if we have an equal number of moles of C2H6 and O2, there is no limiting reactant. No, if you have an equal number of moles, your ratio is 1:1. So B is false. It has to be a ratio of 2 to 7 to be stoichiometric. So this one's false. How about C? If we have masses of C2H6 and O2, there's no limiting reactant. Okay. So how would I approach this one? If the stoichiometry is 2 moles of ethane and 7 moles of oxygen, what is that in relation to mass? 2 moles of ethane would be what? 2 moles of ethane equals, let's see, 1 mole would be 2 carbons, 12.01 times 2, and 6 hydrogens, 6.06. So that'd be 30.08. This would be 30.08. Right. And 7 moles of oxygen would be what? 32 times 7. I get 224. 224 grams of oxygen. That one's not right either, is it? Equal masses. It would be a ratio of 30 to 224 to be stoichiometric. Okay, so this one's wrong. How about D? If we have more mass of O2 than C2H6, C2H6 must be the limiting reactant. No, because the ratio is 224 to 30. If we have more mass of oxygen, it could be 31. It still wouldn't be stoichiometric. And that would make oxygen limiting. Right? Oxygen would be limiting. So the last one, if we have more mass of C2H6 than O2, yeah. If this is greater than that, say it's 225, it would definitely be, oxygen would be limiting because you have excess C2H6. Okay? So this one is correct. That means A is moot. A doesn't mean anything because we did find the correct answer. The key to that one is to recognize in one of them the mole-mole ratio and in the others the mass-mass ratio, which you have to calculate. I think that's it. Yep. That's it. So we'll, Thursday, next Tuesday, I'll be here zoomed in case you have any questions, but you don't have to show up unless you want to take a paper exam. Then I'll be here with the paper. And if paper is more to your liking, come on down. Okay, that's it.